Hiya, so this is day 7 of the 24-day extravaganza. So we are looking today at resistivity and circuit analysis. So what I've got here is I've got a wire probe that is used to measure the rate of corrosion of a pipe carrying a corrosive liquid. The probe is made from the same metal as the pipe, and figure 1 shows the probe. The rate of corrosion is this, the wire is the same as in the pipe. The wire is an unused probe and has a resistance of 0.0070 and a length of 0.5. Calculate the diameter of the wire based on its resistivity. So again, kind of like density, if you see the word resistivity, you should, of course, write down the equation. So, of course, rho equals RA over L. It's asking you to work out the diameter, okay? So I know that's to do with the area. So I know that rho L over R will equal my area. So I'm going to put that in information now. So I've got 9.7 times 10 to the minus 8 times by my length, which is 0.5, over my resistance, which is 0.07. And I get a value for my area of, so 9.7 times 10 to the minus 8 times by 0.5 divided by 0.07. Start again. 9.7 times 10, so 10 to the minus 8 times by 0.5 divided by 0.07. I get an answer of my area of 6.93 times 10 to the minus 7 meters squared. So, of course, my area, because it's talking about a wire. It normally, unless it's otherwise, you normally assume a wire is circular. So that's pi r squared. So I can work out my radius. So divide that by pi, and then square root my answer. My radius is 4.7 times 10 to the minus 4 meters. And of course, the question wants the diameter. This is how they normally trick you. They either give you the diameter or they ask for the diameter. So just be aware of things when you're calculating radii. Did they want the diameter or did they give it to you? So times that by 2, and I get an answer of 9.4 times 10 to the minus 4 meters. So I'm going to check the answer here. Use of the formula, finding the area, and of course getting your area there. So what we've got here is 1 mark for the formula, 1 mark for getting the area or the radius, and 1 mark for the answer there. Okay. So in order to measure the resistance of the probe, it is connected to this circuit here. R3 is adjusted to a particular value, and the current in the cell is 0.66 amps. So it means that the current on this ammeter is 0.66. Okay, so the current in the cell, so the total current of the circuit. What is the total resistance of the circuit? This part's important, assuming that you have negligible internal resistance. Okay, that means you don't have to think of anything else apart from the resistors that are on show. So the total voltage times by the total current times by the equals the total times the total. So V equals IR, Ohm's law. So I know I've got my potential is 1.5, my current is 0.66, my total resistance is going to be 1.5 divided by 0.66, which is going to be 27.27. So 2.27, sorry, 2.27. I knew I was writing there. So 2.27 ohms there. Okay, and that's just simply just worth 1 mark because it's just using V equals IR. Okay, as you can see here, it just gives you 1 mark. The resistance of R2 and the resistance of R3, I'm just going to zoom out a little bit here. The resistance of R2 along this branch and the resistance of R3 is 1.2. Calculate the current in R3. So what actually happens in a circuit is you've got a couple of laws, Kirchhoff's current and Kirchhoff's voltage law. So what actually happens is that electrons will flow either this way around through R2 and R3, okay, and lose a total potential of 1.5 volts, okay, or they will go the other way through this probe up here, through R1 and the probe, and then back through here, and will also lose a total of 1.5 volts of potential, okay. So I know the total amount of potential that is going to be lost over the whole of R2 and R3. And I also know the total amount of resistance over that branch. So I can actually work out the current over that branch. So potential equals IR. So I know the potential we're going to lose is 1.5 is I times the total resistance over that branch, which is going to be 22 plus 1.2. So that's 23.2. So my current is going to be 1.5 divided by 23.2, which is going to be 0.065. Okay. So I know that there's going to be 0.065 amps going through this section, which means here, if 0.66 amps is coming in and 0.065 went there, I know that 0.6-ish, so I've got here 0.595 goes through there. Okay, that is Kirchhoff's current law. Calculate the resistance of the probe when the resistance of R1 is 2.4. So I know that the resistance of R1 is 2.4. Okay, and I know the total current in that section, and I know the total potential in that section. So I could work out the total resistance of that section. So I know I've got 1.5 equals 0.595. Okay, so 0.595 times my total resistance. So I know that the total resistance on that section is going to be a total of 2.52 ohms. So if in total the resistance across that branch of R1 and the probe is 2.52 and the resistance of R1 is 2.4, the probe's resistance is going to be 2.52 take away 2.4, which is going to be 0.12 ohms. Okay, so I'm going to look at the mark scheme here. You get 1 mark for working out the current, and then 1 mark here for working out that the total resistance here, and the resistance of the probe, of course, is 0.12. Okay, so 1 mark, it says 3 mark question, which is quite generous. 1 mark for working out the current here, 1 mark for working out the total resistance, and 1 mark for working out the resistance here. This was only 1, by the way. Okay, so draw all over your circuits. Remember things like Kirchhoff's voltage law, that if I'm doing a loop around, I'm going to lose that potential. So I know I'm going to lose 1 volt of potential in this path and in this path, okay, in total. And I know that when current goes into a node, the current leaving the node is exactly the same that went in. Okay. Calculate the change in diameter when its resistance is increased by 1.6%. Okay, so this thing here, this is quite mean. So this has got resistivity, so we've got R equals RA over L. So R equals rho L over A. Okay. Oh no, potential change in diameter, I do apologize. Oops. Just delete that there. So I've got A equals RL over R, okay? So what's going to happen here is that if my resistance is increasing by 1.6%, okay, which is 1.016, okay, my area will decrease by a factor of 1 over 1.016, okay? And my area equals pi r squared. Okay, so whatever happens to the radius also happens to the diameter here. So if my area is decreasing by that, so 1.016 there, okay, my r, because it's square rooted, my r is going to decrease, okay, by the square root of that. Oops. So my R is going to be 0.99%, 99, so 99% of what it should be, which is a change of 1%. Okay. Oh dear. There you go. So 0.99, which is 1% downwards. Okay. Having a look at your mark scheme here. So I've got a little bit more specific here. So they're saying area decreased by 1.60, so the diameter must decrease by 0.18% here. So what I've done here is I've said, okay, it increased by 0.16 and my area decreases by that. And of course, it'd be the square root of that decrease there. So the square root of 1 over 1.016 is 0.0092. Oh, having a mare with this. 92, which is approximately, I've said about 1%, is asking for a little bit more accurate. So here it's saying that would be a decrease of 0.008, which is a 0.8% decrease there. So the percentage change is 0.8 decrease there. So what I've done here is it's a bit long-winded the way I've done it. It says calculate the percentage change, so it wants a number in this case. And so what I've done is if the R, written the equation out, if R goes up, A goes down by that much. So R goes down and it goes down to 0.992 of it was, which is a decrease of 0.008, which is a decrease of 0.8%. So a bit of a nasty question, but an interesting way of looking at it. Okay. A voltmeter is connected between point A and B. Explain, so if you go out to the circuit, so that it's what happens here, a voltmeter is being connected between here and here. And what it is measuring is it's measuring the difference between the electron's voltage when it gets to this position and the electron's voltage when it gets to this position. So in this consideration, I've got R2, which was, I believe, 22, is that right? Yeah. So I can work out the voltage on R2, so 22 times 0.065. So this is 1.43. Okay, and in this case, R1 was 2.4. So 0.595 times by 2.4 is 1.428. Okay, volts. So what would happen is that remember, this starts with 1.5. As you can see here, I'm measuring the potential difference between these 2 points. Okay. So my electrons come round and it's lost 1.3 volts worth of potential here. And it's got 0.7 left. On this one, it is lost 1.428. So it's got 0.72 left. So this will measure the difference between the energy or the potential that the electrons have at that point. It says here, explain without calculation. So even though it says without calculation, sometimes you can do a little bit of calculation just to help explain what's going on. Why the reading of the voltmeter does not change when the cell is replaced with another cell of the same EMF, but a significant internal resistance. Okay, so why does the voltmeter not change? Even if I added a resistor here, okay, this voltmeter is still measuring what's left after it's gone through R1 and R2. If there was an internal resistor here, okay, that would have taken away, irrespective of which path it went, it would have already taken away an amount of potential, which means that when it goes through here, I'm still going to leave the same proportion here and the same proportion here. Okay, so it doesn't matter if there is an internal resistor because the internal resistor affects all of the current that is going into the circuit. Okay, so the internal resistor affects all of the current that goes through each branch. Okay. This means the share of potential remaining is unchanged, and therefore the voltmeter between A and B will still read the same difference. There we go. So let's actually look at the mark scheme. So this is my explanation of what's going on, but what's the mark scheme second? So any two from the correct reference to lost volts or reduced current, reference to resistors not changing, reference to the voltmeter having high resistance, reference to PD being very small, voltmeter may not be sensitive stuff. So I may have actually dropped a mark here because all I have mentioned is the fact that the share of potential remains unchanged. Okay, the internal resistance affects all the current going through the brush. I'm actually mentioning that it's affecting that. The internal resistance doing one job. This means the share of potential remaining is unchanged, and therefore the potential between A and B will still read the same difference. So, like I said here, I probably would have got only one mark for my explanation, because what the example are looking for here are things like the voltmeter might not be sensitive enough. They're actually looking more of a practical reason than actually the physics is happening. But what I've mentioned here is that I've mentioned that they're both being affected by the reduced current. And I've mentioned that the resistors are not changing. So there is no effect on that split of potential there. So I actually may have still got 2 in this situation. But hopefully by explaining what's going on, and showing you what's actually being measured here, it's really important. It may say without calculation, but sometimes you can, in your head, justify your answer with a bit of calculation. So there we have it. That is day 7 of the 24-day extravaganza. Tune in tomorrow for day 8, which is a third of the way through.